Imagine a bridge so unique, it redefined modern engineering. What if I told you a structure in Maine, built just a few decades ago, holds secrets to groundbreaking construction techniques that still influence bridge design worldwide? Get ready to explore the Penobscot Narrows Bridge, a true marvel of box girder engineering. Welcome to Civil Engineering Edge, where iconic structures meet real engineering insight. Today, we take you on a journey to the heart of one of the most remarkable modern bridges in the world, the Penobscot Narrows Bridge. At first glance, it looks sleek, elegant, and almost effortless. But beneath that graceful form lies a masterpiece of advanced engineering, precision construction, and innovative design thinking. In this video, we embark on a detailed engineering expedition into one of the most iconic modern bridges in North America, the Penobscot Narrows Bridge in Maine, USA. Explore groundbreaking design innovations and uncover how engineers transformed complex theory into a real-world landmark. Whether you're a civil engineering student, a practicing professional, or an infrastructure enthusiast, this deep dive will give you valuable lessons in modern bridge engineering. So fasten your seatbelt, because this is not just a bridge, it's an engineering story worth exploring. Opening the box. Visual and conceptual opening. Visual direction. A sweeping drone shot gliding along the Penobscot River at sunrise. The camera slowly approaches the Penobscot Narrows Bridge, revealing its tall towers and sleek deck. Cut sharply to a dense structural cross-section diagram of a box girder. Looks like a simple bridge, right? Think again. This isn't just a bridge, it's a box of secrets. At first glance, the Penobscot Narrows Bridge appears calm, elegant, and almost minimalistic. Its clean lines, symmetrical towers, and uninterrupted deck give the impression of simplicity. But as every civil engineer knows, simplicity in appearance often hides extraordinary complexity beneath the surface. What you're seeing here is not merely concrete and steel arranged across a river, it's the result of decades of structural evolution, refined analysis, and precision construction. As the camera transitions from the scenic drone shot to a dense engineering drawing, the contrast becomes clear. Behind that smooth deck lies a hollow box girder system, meticulously designed to handle bending moments, torsional stresses, shear forces, wind loads, seismic effects, and long-term durability challenges all at once. This is where engineering stops being just calculations and becomes an art of balance. Box girder bridges are often misunderstood as just hollow beams. In reality, they are highly optimized structural systems where every millimeter of concrete serves a purpose. The Penobscot Narrows Bridge takes this concept to an entirely new level, demonstrating how geometry, material science, and construction sequencing come together to create something both efficient and visually striking. This opening moment sets the tone for the journey ahead. We are not just observing a bridge. We are opening an engineering box filled with lessons on load distribution, redundancy, construction innovation, and long-span behavior. For students, it's a real-world classroom. For professionals, it's a case study in excellence. And for developers and infrastructure planners, it's proof that intelligent design can achieve both performance and beauty. So, as we open the box, prepare to look beyond the surface, because the true brilliance of the Penobscot Narrows Bridge lies within. 1B, introducing the Penobscot Narrows Bridge as a modern engineering marvel. The Penobscot Narrows Bridge, completed in 2006, stands as one of the most remarkable achievements in modern bridge engineering in the United States. Spanning the Penobscot River near Bucksport, Maine, this bridge is not only vital infrastructure, it is a global benchmark in box girder bridge design. With a main span of approximately 354 meters, it ranks among the longest concrete box girder bridges in the world, instantly earning its place in engineering textbooks and professional discussions. What truly sets this bridge apart is its slender profile combined with immense strength. Unlike traditional girder bridges that rely on multiple deep beams, the Penobscot Narrows Bridge employs a single, streamlined box girder deck supported by towering concrete pylons. This creates an uninterrupted visual flow, giving the bridge a sense of lightness despite its massive scale. From an engineering standpoint, the bridge exemplifies efficiency. The box girder form allows the structure to resist torsion exceptionally well, an essential feature for long spans exposed to strong winds, uneven loading, and dynamic forces. This was particularly important at the Penobscot site, where environmental conditions demanded a deck that could perform reliably without excessive maintenance. Another defining feature is the bridge's integrated observation tower, a rare addition that transforms a purely functional structure into a public landmark. This demonstrates how modern civil engineering is no longer just about carrying loads, it's about creating structures that serve communities, inspire confidence, and enhance the surrounding landscape. For civil engineers, the Penobscot Narrows Bridge represents a shift toward optimized concrete structures, where material usage is minimized without compromising safety. For students, it serves as a perfect real-world example of how theoretical concepts like bending moments, torsional rigidity, and press stressing translate into full-scale infrastructure. And for developers and planners, it proves that technically advanced designs can also be economically viable and visually iconic. In short, this bridge is not just modern, it is forward-thinking. It reflects how civil engineering has evolved to meet complex demands with elegant solutions, making the Penobscot Narrows Bridge a true marvel of our time. Teasing the box girder concept, more than just a structural element. Now let's talk about the real star of this structure, the box girder. At its core, a box girder is a hollow structural section, usually rectangular or trapezoidal, designed to efficiently carry loads over long distances. But calling it just a girder does not do justice to its engineering sophistication. In the Penobscot Narrows Bridge, the box girder is far more than a load-carrying element. It is the backbone of the entire structural system. Its closed geometry gives it exceptional torsional stiffness, allowing the bridge deck to resist twisting forces caused by wind, traffic asymmetry, and temperature variations. This is a major advantage over traditional I-girders or T-beams, especially for long spans. The hollow interior of the box girder is not wasted space. It allows for press-stressing tendons, inspection access, drainage systems, and maintenance pathways, all while reducing self-weight. Lower self-weight means smaller foundation forces, reduced material consumption, and greater overall efficiency, key reasons why box girder bridges dominate modern long-span concrete construction. However, this efficiency comes with complexity. Designing a box girder requires advanced analysis, including shear lag effects, torsional warping, and time-dependent behaviors such as creep and shrinkage. Construction is equally demanding, often involving balanced cantilever methods, precision formwork, and strict quality control. The Penobscot Narrows Bridge successfully embraces these challenges, showcasing how careful planning and execution can unlock the full potential of box girder systems. What makes this bridge particularly fascinating is how seamlessly the box girder integrates structural performance with aesthetics. The deck appears thin and elegant, yet it conceals immense strength within. This duality, lightness in appearance, power in performance, is what makes box girder bridges so captivating to engineers. As we move deeper into this video, we'll break open this box girder concept layer by layer, revealing why it has become a cornerstone of modern bridge engineering and why the Penobscot Narrows Bridge stands as one of its finest examples. The anatomy of a box. What is a box girder bridge? Explained simply with relatable analogies. To truly understand the brilliance of the Penobscot Narrows Bridge, we first need to break down one fundamental question: what exactly is a box girder bridge? In the simplest terms, a box girder bridge is a bridge whose main load-carrying element is a hollow box-shaped beam typically made of reinforced or press-dressed concrete, steel, or a combination of both. Unlike solid beams, this girder is empty inside, and that hollow form is not a weakness, it is the source of its strength. Think of a hollow chocolate bar. When you try to bend a solid chocolate bar, it snaps easily. But a hollow chocolate bar, with its material distributed around the edges, resists bending far more effectively while using less chocolate. The same principle applies in structural engineering. By placing material where stresses are highest along the outer surfaces, the box girder achieves maximum strength with minimum weight. Another powerful analogy is an airplane wing. Aircraft wings are not solid slabs of metal. They are hollow structures with stiff outer skins and internal ribs. This allows them to carry enormous loads while remaining light and aerodynamic. Similarly, a box girder bridge deck behaves like a massive horizontal wing, efficiently resisting bending, shear, and torsion. For everyday understanding, imagine standing on a closed cardboard box versus an open sheet of cardboard. The box is dramatically stiffer and harder to deform because its closed shape resists twisting and bending in multiple directions. This is exactly why engineers favor box girders for long spans, curved alignments, and bridges exposed to strong winds. In the Penobscot Narrows Bridge, the box girder acts as the spine of the structure. It supports traffic loads, transfers forces to the towers and piers, and maintains stability under environmental actions. Despite its massive responsibility, it appears slim and elegant proof that intelligent geometry often outperforms brute material strength. By understanding the box girder as a hollow yet powerful structural form, we begin to appreciate why it has become a preferred solution in modern bridge engineering. Inside the box, understanding the internal structure and load distribution, visual direction, transition to a 3D animated cutaway of the Penobscot Narrows Bridge deck, slowly slicing through the box girder to reveal its internal components. When we look inside a box girder, the true sophistication of the system is revealed. A typical concrete box girder consists of top and bottom slabs, connected by vertical or inclined webs, forming a fully enclosed cross-section. This closed geometry is the key to its exceptional structural behavior. The top slab primarily carries traffic loads and distributes them across the width of the bridge. These loads are transferred downward through the webs, which act like vertical walls resisting shear forces. The bottom slab, in turn, resists tensile stresses generated by bending. Together, these elements form a continuous structural loop, allowing forces to flow smoothly and efficiently. One of the greatest advantages of a closed box section is its ability to resist torsion or twisting. In open sections like girders, torsional forces can cause significant deformation. In contrast, the box girder behaves like a closed tube. Twisting forces are distributed around the perimeter, dramatically reducing stress concentrations. 3D animations are especially powerful here. As loads move across the deck, viewers can see how stresses travel along the box girder, wrapping around the section rather than concentrating at a single point. This explains why box girder bridges perform exceptionally well under asymmetric traffic loading, wind, and seismic actions. Inside the box girder, engineers also place press-stressing tendons, usually running longitudinally along the span. These tendons introduce compressive forces that counteract tensile stresses caused by bending, significantly increasing load capacity and durability. The hollow interior allows space for inspection walkways, drainage pipes, and maintenance access features that are impossible in solid beams. In the Penobscot Narrows Bridge, this internal efficiency allows the deck to remain slender while spanning extraordinary distances. Every component inside the box has a defined role, and nothing is redundant. The result is a structure that is not only strong, but also predictable, controllable, and long-lasting. Understanding this internal anatomy helps engineers appreciate why box girders are not just strong, they are intelligently strong. Box girder versus traditional bridge types, a structural comparison. To fully appreciate the advantages of box girder bridges, it helps to compare them with more traditional bridge systems such as truss bridges and suspension bridges. Truss bridges rely on a network of triangular elements to carry loads. While extremely effective for certain spans, trusses are visually complex, require numerous connections, and are often maintenance-intensive due to exposed members. Box girder bridges, by contrast, use continuous solid surfaces, offering better durability and reduced long-term maintenance. Suspension bridges excel at ultra-long spans, using cables to transfer loads to massive anchorages. However, they demand extensive structural depth above and below the deck, complex aerodynamic design, and high construction costs. Box girder bridges cannot match the span lengths of suspension bridges, but within their optimal range, they offer a far more economical and stiff solution, especially for concrete construction. From a structural behavior perspective, traditional girder bridges using I-sections are efficient for short spans, but struggle with torsion and wide decks. Box girders overcome this limitation through their closed geometry, making them ideal for curved bridges, wide carriageways, and bridges subjected to uneven loading. That said, box girder bridges come with their own challenges. Design analysis is more complex, requiring advanced modeling to account for shear lag, torsion, creep, and shrinkage. Construction demands precision formwork, strict quality control, and skilled labor. These factors can increase initial costs, but the long-term benefits often outweigh them. The Penobscot Narrows Bridge represents the sweet spot of box girder application. It achieves long spans without the visual clutter of trusses or the extreme complexity of suspension systems. The result is a bridge that is structurally efficient, aesthetically refined, and economically rational. In modern civil engineering, box girders are not a replacement for all bridge types, but where conditions are right, they are often the most intelligent choice. Building the impossible. Innovative construction techniques, fabrication, and assembly of box girder sections. Constructing the Penobscot Narrows Bridge was not a matter of simply pouring concrete in place. It required a carefully orchestrated sequence of advanced construction techniques, many of which represent best practices in modern box girder bridge engineering. At the heart of this process was the segmental construction method, chosen for its precision, safety, and efficiency over long spans. The box girder deck was built using precast concrete segments, each fabricated under controlled conditions to ensure consistent quality, dimensional accuracy, and material performance. These segments were cast in specialized yards where concrete strength, curing temperature, reinforcement placement, and press-dressing ducts could be monitored with extreme precision. Each segment functioned like a piece of a massive three-dimensional puzzle, designed to fit seamlessly with the next. Once fabricated, the segments were transported to the site and assembled using the balanced cantilever method. Starting from the bridge pylons, segments were added symmetrically on both sides, maintaining equilibrium and minimizing bending moments during construction. Temporary post-tensioning tendons held the segments together until permanent press dressing was applied, transforming individual units into a continuous structural system. The box girder's hollow design played a critical role during construction. It reduced self-weight, allowing longer cantilever lengths and smaller lifting requirements. Inside the box, engineers installed longitudinal press-dressing tendons, which compressed the concrete and enhanced load capacity. This internal press-dressing system ensured that once the deck was complete, it behaved as a single monolithic structure rather than a collection of segments. What makes this construction process truly innovative is the level of engineering foresight involved. Every construction stage was analyzed independently to ensure stability, stress control, and geometric accuracy. The Penobscot Narrows Bridge demonstrates how modern civil engineering transforms complex theoretical principles into practical, buildable reality, overcoming construction challenges, precision, environment, and scale. Building a bridge of this scale is never without challenges, and the Penobscot Narrows Bridge presented some of the most demanding conditions a construction team could face. One of the most significant obstacles was the harsh environmental setting of coastal Maine. Strong winds, freezing temperatures, and seasonal storms placed constant pressure on construction schedules and safety protocols. Concrete construction in cold climates requires meticulous temperature control. Improper curing could compromise strength and durability, so engineers implemented advanced curing techniques, including thermal blankets and controlled curing environments, to maintain concrete quality. Wind effects were another major concern, especially during segment lifting operations, where even slight movements could result in misalignment. Precision was critical. Each precast segment weighed several hundred tons and had to be positioned within millimeter-level tolerances. A minor misalignment could propagate through the structure, affecting geometry and load distribution. Surveying teams worked continuously using high-precision instruments to verify alignment, elevation, and rotation at every stage. Another challenge was the connection between segments. Epoxy joints were used to bond segments together, requiring flawless surface preparation and strict quality control. Press-dressing tendons had to be threaded and tensioned with extreme accuracy to achieve the desired compressive forces without overstressing the concrete. Logistics also posed significant difficulties. Transporting massive segments, coordinating cranes, and managing construction equipment on a narrow work site required exceptional planning. Every operation had to be sequenced carefully to avoid delays and ensure worker safety. These challenges were not obstacles, they were tests of engineering discipline. The successful completion of the Penobscot Narrows Bridge is proof that meticulous planning, skilled execution, and adaptability are as critical as design itself. Visualizing human ingenuity, archival footage, and construction scale. Visual cue. Archival footage shows massive cranes lifting concrete segments against a dramatic sky, workers guiding them into position, and engineers studying drawings on site. When we look at archival footage of the Penobscot Narrows Bridge under construction, one thing becomes immediately clear: this was not just a technical achievement, but a human one. Towering cranes, massive concrete segments suspended in midair, and teams of engineers and workers collaborating in perfect coordination tell a powerful story of ingenuity and determination. Each image captures the sheer scale of the operation. Individual segments, each weighing hundreds of tons, appear almost fragile as they are lifted high above the river. Workers, dwarfed by the structure, guide these elements into place with hand signals and radio communication, demonstrating the precision and trust required in large-scale construction. Still images of the bridge during different construction stages reveal how the balanced cantilever method transforms an empty river crossing into a soaring structure. Segment by segment, the deck extends outward, seemingly defying gravity. This visual progression makes abstract engineering concepts tangible, allowing viewers to see theory become reality. Archival footage also highlights the collaboration between disciplines. Structural engineers, surveyors, crane operators, concrete specialists, and safety teams all played essential roles. Every lift, every connection, and every press-dressing operation required coordination and expertise. These visuals are more than historical records, they are educational tools. They remind us that behind every iconic bridge lies thousands of decisions, countless calculations, and the dedication of skilled professionals. The Penobscot Narrows Bridge stands today not only as a structural landmark, but as a tribute to what civil engineers and construction teams can achieve when innovation meets execution. Beyond the blue, design innovations. Design innovations that set the Penobscot Narrows Bridge apart? While the box girder deck is the structural backbone of the Penobscot Narrows Bridge, what truly elevates this structure into the realm of engineering excellence is the integration of multiple innovative design elements working together as a unified system. This bridge is not merely a box girder bridge, it is a cable-stayed box girder bridge, a hybrid configuration that brings together the best features of both systems. The most visually striking innovation is the single plane cable stay arrangement. Instead of using multiple planes of cables, the Penobscot Narrows Bridge employs a central plane of stay cables anchored to tall concrete pylons. This arrangement reduces visual clutter while maintaining excellent structural performance. The cables directly support the box girder deck, significantly reducing bending moments and allowing for a slimmer deck profile. Aesthetically, the bridge is a masterpiece of restraint. The slender pylons, clean cable geometry, and uninterrupted deck create a sense of elegance that complements the surrounding landscape. The designers intentionally avoided heavy superstructure elements, allowing the structural form itself to become the visual identity of the bridge. This philosophy, where structure and architecture merge seamlessly, is a hallmark of modern bridge design. Another notable innovation is the integration of an observation tower within one of the pylons. This is a rare feature in major bridges and demonstrates how infrastructure can serve both functional and civic purposes. From an engineering perspective, this required careful consideration of additional loads, vibration control, and safety without compromising structural integrity. Material optimization also played a crucial role. High-performance concrete was used to achieve strength, durability, and long-term resistance to environmental exposure. Every design choice, whether structural or aesthetic, was made with efficiency in mind, ensuring that no element was decorative without also being functional. Together, these innovations make the Penobscot Narrows Bridge not just distinctive, but forward-looking, a model for how modern bridges can combine beauty, efficiency, and innovation. Structural benefits, rigidity, torsion control, and durability. Beyond visual elegance, the design innovations of the Penobscot Narrows Bridge deliver significant structural performance benefits. One of the most important advantages is increased rigidity, achieved through the combined action of the box girder deck and the cable stay system. This hybrid configuration allows loads to be shared efficiently between the deck, cables, pylons, and foundations. The closed cross-section of the box girder provides exceptional torsional resistance, a critical requirement for long spans subjected to wind, uneven traffic loading, and temperature gradients. When combined with cable stays, which reduce bending moments in the deck, the result is a structure that remains stable under complex loading conditions. The bridge's resistance to dynamic forces is another key benefit. Wind-induced vibrations, traffic-generated oscillations, and thermal movements are effectively controlled through careful detailing and material selection. The box girder's mass provides inherent damping, while the stay cables contribute to stiffness and load redistribution. Durability was a central design objective. The use of high-quality concrete, protective detailing, and minimized exposed components significantly reduces maintenance demands. Unlike truss bridges with numerous joints and exposed steel elements, the Penobscot Narrows Bridge features smooth surfaces that are less susceptible to corrosion and fatigue. Press dressing within the box girder further enhances durability by keeping concrete primarily in compression, limiting crack formation and protecting reinforcement from moisture ingress. This approach extends service life and ensures predictable long-term behavior. From a life cycle perspective, these design choices translate into lower maintenance costs, improved safety, and consistent performance over decades. The bridge is not only strong at the time of construction, it is designed to remain strong throughout its entire lifespan. Influence on modern bridge engineering and future projects. The Penobscot Narrows Bridge has had a lasting impact on the field of bridge engineering, serving as a benchmark for hybrid bridge design. Its success demonstrated that cable-stayed box girder systems are not only feasible but highly efficient for long-span concrete bridges. Following its completion, engineers and designers worldwide began adopting similar design philosophies favoring slender decks, integrated structural systems, and aesthetic simplicity. The bridge reinforced the idea that structural efficiency and visual appeal do not need to be competing objectives. In academic circles, the Penobscot Narrows Bridge is frequently referenced as a case study in advanced structural analysis, construction sequencing, and life cycle design. It has influenced design guidelines related to torsional behavior, press stressing strategies, and hybrid systems, shaping how modern bridges are conceived and analyzed. The bridge also set new expectations for public infrastructure. By integrating functionality with architectural elegance and public access features, it redefined what a bridge could represent within a community. This holistic approach has inspired infrastructure projects that prioritize both engineering excellence and civic value. Perhaps most importantly, the Penobscot Narrows Bridge proved that innovation does not require radical reinvention, it requires intelligent integration of proven concepts. By combining box girders, cable stays, advanced materials, and thoughtful aesthetics, the bridge established a design language that continues to influence projects across the globe. For today's civil engineers and students, it stands as a reminder that the future of bridge engineering lies not in isolated innovations, but in how those innovations are brought together to create structures that are efficient, durable, and inspiring. The legacy of the Penobscot, a lasting impact. Infrastructure meets architecture. The Penobscot Narrows Bridge stands today as far more than a river crossing. It is a lasting symbol of how modern civil engineering can seamlessly merge function with form. From an infrastructure standpoint, the bridge fulfills its primary mission with exceptional efficiency, providing a safe, durable, and high-capacity transportation link across the Penobscot River. Yet what truly elevates it beyond utility is its architectural presence and enduring relevance. Structurally, the bridge has proven the effectiveness of box girder and cable-stayed hybrid systems, delivering consistent performance under traffic, wind, and environmental loads. Its design anticipated long-term behavior, accounting for creep, shrinkage, fatigue, and durability factors that define whether a bridge merely survives or truly endures. Years after completion, the Penobscot Narrows Bridge continues to perform as intended, validating the engineering decisions made during its conception. Architecturally, the bridge has become an unmistakable landmark. Its slender deck, soaring pylons, and graceful cable arrangement create a visual identity that is both modern and timeless. Unlike structures that age poorly or feel dated, the Penobscot Narrows Bridge retains a sense of relevance and indication of thoughtful, restrained design rather than fleeting trends. For civil engineers, this bridge represents a case study in balancing economy with ambition, strength with elegance, and innovation with reliability. For students, it serves as a real-world example of how theoretical principles evolve into iconic infrastructure. And for the general public, it stands as a quiet but powerful reminder that engineering excellence can enrich everyday life. In this way, the Penobscot Narrows Bridge has secured its legacy not just as a structure that works, but as a structure that inspires, connecting communities, economic and regional significance. Beyond its technical brilliance, the Penobscot Narrows Bridge has played a transformative role in the social and economic life of the region. By replacing an older, less efficient crossing, the bridge dramatically improved connectivity between communities on either side of the river, reducing travel times and increasing reliability. For local residents, the bridge simplified daily commuting, making access to jobs, education, and services more efficient. For businesses, improved transportation infrastructure translated into lower logistics costs, increased mobility, and greater economic opportunity. The bridge became a catalyst for regional development, supporting industries such as manufacturing, tourism, and trade. One of the most unique aspects of the Penobscot Narrows Bridge is its integration into the local cultural landscape. The observation tower attracts visitors from around the world, transforming the bridge into a destination rather than merely a passageway. Tourism associated with the bridge contributes to the local economy while raising public appreciation for civil engineering achievements. From a planning perspective, the bridge demonstrates how strategic infrastructure investment can deliver long-term economic returns. Rather than serving only immediate transportation needs, it was designed with future growth in mind, ensuring capacity, durability, and adaptability over decades. The Penobscot Narrows Bridge also strengthened regional identity. It became a shared symbol of progress, pride, and resilience. In connecting places, it also connected people, linking communities not just physically, but socially and economically. More than a bridge, a testament to human ingenuity. As we reflect on the Penobscot Narrows Bridge, one truth becomes clear: this is not just a bridge. It is a testament to what human ingenuity can achieve when creativity, science, and discipline converge. Every aspect of the bridge, from its box girder deck to its cable stays, from its construction methodology to its aesthetic restraint, tells a story of problem solving at the highest level. It represents thousands of hours of analysis, design iteration, field coordination, and craftsmanship. Behind the concrete and steel are engineers, planners, surveyors, construction workers, and visionaries who transformed an idea into reality. For civil engineers, the bridge stands as a reminder of the profession's responsibility and power. It shows that engineering is not merely about calculations, it is about shaping the built environment in ways that endure. For students, it is a source of motivation, demonstrating that the concepts learned in classrooms can one day become structures that define landscapes. For society, it is a quiet monument to human capability. As the sun sets over the Penobscot River and vehicles glide across the deck, the bridge continues to perform its role effortlessly. Yet beneath that calm surface lies an extraordinary story of innovation and ambition. The Penobscot Narrows Bridge invites us to look closer, to appreciate the intelligence embedded within its form, and to feel a sense of awe at what thoughtful engineering can accomplish. In the end, this bridge does more than connect to shores, it connects ideas to reality, engineering to art, and the present to the future. As we conclude our journey across the Penobscot Narrows Bridge, one thing becomes clear: this structure is far more than concrete, cables, and calculations. It represents the power of innovative thinking, disciplined engineering, and human collaboration at its finest. From its elegant box girder deck to its lasting impact on the community, the bridge stands as a timeless lesson in how infrastructure can be both functional and inspiring. For civil engineers, it is a benchmark of excellence. For students, a real-world classroom, and for society, a symbol of progress. If this video expanded your understanding of modern bridge design, don't forget to like, share, and subscribe to Civil Engineering Edge, where we continue to explore the structures that shape our world. Until next time, keep learning, keep building, and keep pushing the edge of engineering.